All right, today we have a topic before us, design of combined footing. And we have a footing we intend to design that is going to be supporting two columns A and B. And we have been given the loads on the column, the service load on column A, we have it as 900 kilonewton. The ultimate load at column A, we have it as 1,400 kilonewton. And equally, their service bending moment, we have that of A60, we have that of ultimate moment for A to be 90, and the load on column B, service load 1,120 kilonewton, ultimate load 1,600, service moment 18 kilonewton meter, ultimate moment 120 kilonewton meter. Now the combined footing will be supported at a depth in the soil which is not known and not stated, and the unit weight of the soil is 20 kilonewton per cubic meter. We have the internal angle of friction to be 30 degrees and the shear stress coefficient to be 10 kilonewton per meter square. The footing will be designed against a factor of safety of 3.0 against bearing capacity failure, and the design parameters, characteristics cube strength of steel has been given, 410 Newton meter per millimeter square, and that of concrete, 25 Newton per millimeter square. Now the columns are of size 300 by 300, so they are made up of square columns. So we're going to commence the design by first of all sizing of the footing. And we'll look at certain scenarios before going into the design. Now let's go over to the design. All right, so we are going to look at the footing. We've already chosen a depth for the foundation, and we have the depth of the foundation to be 1.5 meter deep. Now let's assume that, and in proportioning the footing, we must. Hey, you are making noise. No noise. All right, so in proportioning the footing, we are going to make use of the punching shear criteria. Now, note from the punching shear criteria, we are having from the face of the column, according to the British standard, we have 1.5H on each side of the face of the column to the critical perimeter. So this is a critical perimeter, this area is a critical perimeter. So we have the distance from the face of the column to the critical perimeter as 1.5H on both sides. And we have a similar thing on the other side. So if we want to design this footing so that we have, if we want to design this footing so that we have a little cantilever from the face of the column, let's say 600 on this way, 600 this way, 600 this way, so that we have that cantilever from the face of the column. We're going to have it as this. Remember that for tension, our tension reinforcement must move beyond this critical perimeter, okay? So if our tension reinforcement must move beyond the critical perimeter, it means that the minimum length of our footing is going to be this area plus the critical perimeter, the distance from the critical perimeter, which is this point, and this point on this side. So we have 1.5H this way, 1.5H this way. So if we add it up to 3.8, we'll have the total minimum length to be what? 3.8 plus 3H, okay? So with this, we can choose a length for this footing. Having known our H, for any value of H chosen, we can conveniently pick a satisfactory length for the footing. A similar way also, we can do the same for the width. On the width side of the footing, we have from here to here 1.5H. So that is the minimum, here to here 1.5H. So if we add it up, we have 3H plus the column length or width. You add it up, we're going to have 300, which is the column size, plus 3H. So that gives us the minimum breadth that the footing can take. And if that is the case, we can choose a breadth that is greater than this. Similarly, also we can do the same for that of the length. Okay. Now, there are other options that can be taken when it comes to the design of footing. We can decide to have our footing so that one side of the column align with the edge of the footing. This is very essential in the case of a property line, where we have a property line where we can have the foundation of the property to to uh, to in, to interlap or to lap or to intersect with the foundation of our footing. If we are to design as an isolated part footing, then we must avoid that uh, interlapping or that lapping or that all right, we must avoid that. So we must ensure that we push our footing so that the footing foundation does not spread beyond any kind of property line. So we can have that option, call it option 2. This could be an option 1. Now the third option we are going to look at is the trapezoidal shape footing. Now the trapezoidal shape footing is very, very, very important when it comes to the issue of property line. It's very, very efficient. We are going to speak more on that in whenever we are doing we're going to speak more on that when we are treating the design of trapezoidal footing. Okay, so that is another option, option 3. Now we come to BS 8110/1997. Remember that the code BS 8110/1997 states that the shear force, the punching shear, should be measured at a distance of 1.5 D from the face of the column, and that is a recent version of the British code. And also remember, what we are using is the earlier version, which says 1.5H. Now we looked at the Eurocode 2. Eurocode 2 has its own version for this. And for Eurocode 2, it says that from the face of the column to the critical perimeter should be taken as 2D. So whichever code you are using, the same principle can be applied. All right. So let's go over and do the sizing of this particular footing. What we want to do is to proportion this footing. Now, in proportioning the footing, like we did from our BS 8110, we know that the breadth of the footing, like I've explained before, should be greater than the column size plus 3H. So if we do that, we're going to have the breadth of the footing to be 1,200 mm. Now, we say let's choose a breadth of footing to be 1,600 mm. Now, if we do that, we have our breadth of footing here. Now, the next, we are going to take the length of the footing. Say, take the minimum length of footing to be equal to, of course, like I've illustrated, you know that the minimum length becomes 3.8 plus 1.5H on one side and 1.5H on the other side. So we have it eventually to be 4,400 mm. And we can say, okay, let's take our dimension of footing. Let's choose a length of 5,000 mm. Okay, so the next step we want to take is mm. The next is, we say that a footing of 1,600 mm by 5,000 mm by 0.3 meter is adequate for stability of this foundation. Now, the next stage is the determination of the bearing capacity of the soil. We've been given all the geotechnical parameters for the determination of the bearing capacity. The internal angle of friction, we'll have it to be 30. We'll have the unit weight of soil. The depth of the soil has not been given, but we are going to assume the depth of the soil to be 1.5 meters from the ground level. All right. Now, having made that assumption, we are using the Tazaki's bearing capacity formula. Of course, the Tazaki's general formula for bearing capacity determination, we have it on the board here as the general formula. Of course, we know that we have the shape factors, Tazaki shape factors, XC, we have X gamma, and we have SQ. Of course, B over L, which represents the aspect ratio, the breadth over the length. We've already chosen the breadth to be 1.6 meters, and we have the breadth to be 5 meters, okay? So we are going to substitute them into our shape factors. If we do that, we'll have XC to be 1.096. We have X gamma to be 0.936. We have SQ to be 1.0. Okay, so we have SQ to be 1.0. All right. Now, the internal angle of friction from our table, from Kazaki's table, you can check that table out. For an internal angle of friction of 30 degrees, we have Kazaki's coefficient NC to be 37.2. We have NQ to be 22.5, and we have N gamma to be 19.7. All right. So these are the parameters we've gotten from the table. Okay. So now let's go over to determine the bearing capacity of this foundation. All right. So we discovered that the net bearing capacity is 1,347.7112 kilonewton per meter square. Now we have the allowable soil bearing capacity by dividing it by a factor of safety that has been given the question 3.0. If we do that, we are going to have the allowable bearing capacity to be 449.2 kilonewton per meter square. Now, the next stage is stability check. We are going to check for stability. Stage is stability check. We are going to check for stability of the footing. We say the footing self-weight, we have it to be 57.6 kilonewton. We have the total vertical load, total service vertical load to be 207.6 kilonewton. Now, I say for stability requirement, the total service load or service pressure should be less than the allowable soil pressure, which is the allowable soil bearing capacity of the soil. Okay, so based on that, we are going to determine the service pressure. We have the loads as arranged on the footing. We have the total length of the footing remains 5 meters. We have a clockwise moment 60 kilonewton meters. We have an anti-clockwise moment of 80 kilonewton meters. We have a service point load of 900 kilonewton. We have on this side, which is at point B, we have it as 1,120 kilonewton. At point A, we have 900 kilonewton. Now, the total self-weight of the footing is 57.6. Now, we say let the total resultant load be acting on our right-hand side at an eccentricity EX, which we do not know. So since we do not know EX, we are going to say that let that resultant load be acting at a distance y from the point C. Let's call from here to here C, which is the distance at which our total resultant load is acting. Remember, the total resultant load is going to be in the reverse direction because in order to keep this system in equilibrium, the resultant load should be in the opposite direction. That's why we're having it on this side. So we already have an eccentricity, and we are saying that let that resultant load be acting at an unknown distance y from the point C. So from here to this point, we are calling it y. So having done that, the next thing we are going to do is to take moment about point C. So if we take the algebraic sum of moment about point C to be 0, we have the anti-clockwise moment, all anti-clockwise moment positive, negative, and we have clockwise moment to be positive. So if we solve that amicably, we are going to solve it and obtain our y. Once we have our y, we can therefore obtain our ax. Okay. Look at the determination of our y. So like we have it here, summation of moment about point C to be 0. So if we do that, we're going to have our y to be 2.6915 meters. Okay. So if from this point to this point is 2.6915, it means from here to here, all we need to do is to subtract this, say y minus 2.5 to give us EX. So we are saying that EX is 0.1915 meters, okay? Now the base reactive pressure, like we normally do it, we'll have this base reactive pressure. The maximum base reactive pressure, we're having it to be 319.37 kilonewton per meter square. We are not going to consider the minimum pressure because at this point, we just want to be sure that our dimension of 1.6 meter by 5 meter by 0.3 meter is adequate for stability. So once we discover that this is less, like we have discovered, our Q allowable is 449 kilonewton per meter, and we have this to be 319. So we can therefore boldly say that our choosing dimension of 1.6 meter by 5 meter by 0.3 meter is adequate adequate instability. The next stage we are going to go into is the design of the footing for ultimate load. Now, the design of the footing for the same thing we are going to do to obtain the ultimate pressure, which is the same as the base reactive pressure. So, like we have it as usual, we have our eccentricity. Assume our load acting at this point. So, we are going to do that. We are going to obtain the distance, which is from here. Let's call that y1 from the point of our resultant load to our point C again. So we'll take the same procedures like we did in this one and obtain the service, the ultimate pressure that is acting on the foot. Of course, this is the pressure we're going to use to design the footing. Okay, so let's do that as we work on this one. All right, so summation of moment about point C, we are going to have it to 0. Now we have the anti-clockwise moment about point C. Remember from the diagram, it's going to be a negative moment because it's an anti-clockwise moment. So the point Y remains. So to do that, we have 308.6 Y plus a clockwise moment 90 plus another clockwise moment 1400 times 0.6. For work that out, we have an anti-clockwise movement of 120. So for work that out, we're going to have 2.163 meters. So we say that the centroid, the eccentricity from the centroid becomes 2.613 minus 2.5 and is equal to 0.1136 meters. Okay, so this is what we have as our eccentricity. Now the next is to calculate the base reactive pressure. The base reactive pressure, substituting our value, this is the total load divided by the area and our eccentricity. So if we do that, we're going to have the maximum base reactive pressure to be 37.568 kilonewton per meter square. And we'll have the minimum pressure to be 332.581 kilonewton per meter square. So this is what we have as the base reactive pressure from the soil. Now, drawing the footing again, we know that from here to here is 1.9, 1.9. We have the diagram as shown. Now, the step weight of the footing, we already know is 80.61, 80.6 kilonewton. So we have that step weight. What we want to do at this point in time, we are going to minus the pressure due to self weight. Remember, the self weight is coming down, and we're going to minus that pressure because it's going to be coming against a pressure that is net upward pressure. So let's do that. This is 80.6 kilonewton. If we convert it to pressure, we're going to have it 80 divided by 1.6 and by 5. We're going to have 10.075 kilonewton per meter square as the pressure. Now, if we have that as the pressure, we just need to minus that figure from maximum pressure 437 and 332.58. So if we do that, we're going to have the net pressure to become 322.506 and 427.495 kilonewton. These are the net pressure. I haven't subtracted the pressure due to self weight of our footing. Okay. Now, the moment have been placed as we have them. There is a triangular load. So of course, we are going to make do with similar triangle to have the gradient or the slope of this. If you make use of similar triangle, you are going to have, for call anywhere here y, we are going to have the difference between this and this is 104.989. So we have the difference as this. So what we need to do is to divide it by 5. So if we're taking an expression of x, an arbitrary value for x along any point, we're going to have the expression to be 104.98 divided by our 5. Okay, so that is the expression for the slope in terms of an unknown distance x. So now let's say we want to take load zones using the unknown x. Now if we take the value of the load zone between 0 to 0.6, we can write the expression as this. This is an ordinary UDL. So this UDL multiplied by our arbitrary point x. So if we multiply by arbitrary point x plus as the area of this triangle, let's assume we are cutting a section across this point. All right. The area of this triangle is what we're going to determine. So the area of this point from here down to here is 104.98 9x over 5. So if from here to here becomes our x, we have this value as uh, the intensity at this point. Okay, so if we do that, the area of this little triangle at this point becomes half base times height, where this represent the height, x represent the base. So we have 0.5 times half base times height. So that is why we have this expression. So the final expression for shear becomes this. Uh, we have that of moment. We'll do the same for moment. Remember, when we integrate the shear force expression, we are going to have the moment expression, which we've just gotten here, to be 161,253 x squared plus 3.499 x raised to the power 3. Okay, so now having gotten the expression for both shear and moment, we have to substitute value between 0 to 0.6. So I say when x is 0, we have the shear force to be 0. When x is 0.6, we have the shear force to be 197.28 kilonewton. When x is uh, when x is 0.6, the moment becomes 5.88 kilonewton. When x is 0, the moment is 0. So we have 58.806 kilonewton per kilonewton meter per meter. Remember, it's per meter because we've already divided our load into linear uh, meter. Okay, so the next zone, low zone, we're going to take the next low zone so that we'll get the next expression and also the moment values and shear force values. All right, so the next low zone, we have it to be at this point. So we have the next low zone to be at this point. Now, if you look at the zone, we are going to have the moment at this point, taking an expression, taking the moment, the shear force expression in terms of S, it remains what it is like we did in zone between 0 to 6. It remains the same. But the only difference we're going to have here, remember, if you cut across between this zone and this zone, you're going to have 1,400 kilonewton as another force that is acting. All right, so that is a line load, remember. So it's a line load. We are dividing it by the width of the footing. Okay, so we have this as the figure. Now the next phase we are going to take is to substitute value for the shear force along the zone between 0.6 to 4.4. So if we do that, we'll have the shear force around here to be when x is 0.6, I will substitute it here. We're going to have the shear force value to be 677.716 kilonewton. Now the next is when s is 4.4. If we substitute that value, we're going to have 747.28 kilonewton as the shear force. So we've got the shear force for the two extreme end of this load zone. Now the next we're going to do is to get the moment for the two extreme end. And having gotten the moment, we are still going to obtain the maximum moment between this zone. Okay, so we say the maximum moment, the moment at 0.6. If we do that, we're going to have that moment to be 115.056 kilonewton meter per meter. When x is 4.4, we'll have that moment to be 151.16 kilonewton per meter. So we've done that. So the next is to determine the maximum moment. Obtaining the maximum moment along this particular span, of course, we know that maximum moment occurs where shear force is 0. So equating our shear force expression to be 0. All right, so determining the maximum moment at the point where shear force is 0. If we do that, we are going to equate our shear force expression. These are shear force expression. So if we equate this shear force expression, we are going to have the point of maximum moment is at a point that is 2.508 meters from the end of C, point C, which is at this point. Okay, so that is where we have the maximum moment. So we're going to substitute this value of 2.508 All right, so the point of maximum moment, if we solve that, we're going to have the maximum moment to be negative 543.759 kilonewton per meter. Now, how we go to the maximum moment between that span um, 0.6 to 4.4. The next, we are going to go to the next low zone, which is the zone 4.4 to. All right, so the maximum moment, we are going to have the maximum moment to be negative 543.759 kilonewton per meter, kilonewton meter per meter. Now we come to the second zone, which is zone between 4.4 and 4.5. We redraw the diagram. This is the section we are cutting through, section YY. Now, if we cut the section YY, we have the same thing. At this time, we are going to have a load of 1,400 and 1,600 participating. And we have the moment, positive and negative moment. Both of them will be divided by the width of the slab. So remember, is a line moment. So we'll have it as this. So if we solve that, we are going to have the expression as this. Now, this is the expression for the shear force. So we have, when S is 4.4, we have the shear force to be negative 252.71 kilonewton. When S is 5, we have the shear force to be 0. And when X is, the moment expression becomes this. Let's get the moment expression. This is the moment expression. Now, substitute the value when X is equal to, when S is equal to 5, you will see that the moment at that point is 0, which conforms to the actual situation. Now, we need to obtain the value. It seems we've not gotten value for moment at 0.4. 0.4. So let's substitute that for that point. Moment for n. Now, at the last part, we're going to solve when x is equals to 4.4, which is at this support edge. If we work that out, we're going to have the value for moment to be 76.166. All right. So this brings us to the conclusion and the end of the determination of the bending moment and the shear force. So quickly, let's draw the diagrams, the bending moment diagrams and the shear force diagram, and we'll proceed further into the design proper. All right, so looking at the board, you're going to see the bending moment and the shear force diagram being drawn on the board. So having done this, the next phase is to carry out the design. Now, because of the voluminous nature of this design, we are not going to cover that in this video. You check the comment section and you can check out the part 2 of this design in that section. We're going to design it, whichever code you are using, the principles remains the same. We're going to carry the design out from that point. So do well to hit the subscribe button if you find this lecture very helpful. Thank you very much for watching. I'll see you in the next part of this series. Have a wonderful time.